Born in 1791, the son of a blacksmith, Michael Faraday received little formal education, but would go on to revolutionize the world. His original laboratory still exists at London's Royal Institution.
If I give it a little push.
Where physicist Andrew Steele is exploring how Faraday's discoveries made magnetic levitation possible.
Faraday's discoveries revolutionised our understanding of the interplay between electricity and magnetism. And one of the things that this understanding allows us to make is an electromagnet. So an electromagnet is made of a coil of wire. You then need to get the ends of those pieces of wire and plug them into a power supply. And finally, to magnify the magnetic effect, you often place a core of a material like iron in the middle of the magnet. Let's connect this up. And to prove to you that that's magnetic, you can see that even with this extremely simple setup, we can actually get a piece of metal to stick to it. Another crucial fact about electromagnets, if you want to use them for levitation, is that we can change their strength, and we can do that very easily. Just by changing the electric current passing through this magnet, I can turn the current down and make the attraction much weaker, or I can turn the current up and make that attraction get stronger again.
Not only can electromagnets be adjusted or turned on or off at will, but they can also be significantly stronger than ordinary magnets.
If you want to suspend an entire train, you're going to need a pretty powerful electromagnet. And actually, electromagnets are pretty strong. This little one is enough to suspend my entire body weight. And actually, this thing needs surprisingly little electric current. There's less electricity flowing through this device than there is through your hairdryer or your kettle at home. We've got an electrical current flowing through this electromagnet. If we connect it to the piece of metal on my back, then hopefully there should be enough strength to hold me above the floor. And there you have it.
On the Shanghai Maglev, banks of powerful electromagnets are installed into units that sit on the underside of the carriages. Guidance magnets keep the train centred, and support magnets attract the unit to the underside of the track, and so lift the train above. The entire train therefore effectively flies, suspended 10 millimeters below the track. Not only does this make for extremely fast, friction-free travel, but also reduces wear and tear.
Because there's no contact between the train and the guideway, there is no friction, and this means that the train can have a lifetime of up to 50 years with minimum maintenance required.
But to create a train fit for the future, its designers would still have to look to one of history's greatest innovators.
When I put it on the motor and switch on the magnets, something pretty dramatic occurs.
To create yet more impossible engineering. Travelling at an astonishing 431 kilometers per hour, whilst floating on a magnetic field. The Shanghai Maglev is the only high-speed train of its kind operating commercially in the world. But to create this wonder of modern engineering, its German developers would need to overcome some seemingly impossible engineering challenges. Including creating a propulsion system in tune with its futuristic home.
China, like all modern economies, is worried about its carbon emission quota. As development continues, the demand for oil will also likely increase. But China has a limited domestic oil supply. With its current gas-guzzling congestion problems, greener transport initiatives are drastically needed. Otherwise, the city will choke.
The solution would have been impossible without one of history's great engineering innovators. In the late 1940s, one British engineer's experiments would ultimately earn him the nickname the father of maglev.
This is a sheet of aluminium. When I put it on the motor and switch on the magnets, something pretty dramatic occurs.
Electrical genius Eric Laithwaite developed the first practical linear electric motor, creating an effect he later dubbed the magnetic river.
First of all, it will levitate or support an aluminium plate. It will guide it sideways, and it will also propel it along.
The linear motor essentially takes a traditional coiled electric motor and unrolls it. Instead of spinning a rotor, what was the coil or stator provides a bed that drives the object along its length.
And there you have your modern vehicle being guided, lifted, and propelled, all by means of the same set of coils.
Laithwaite's experiments provided the key that unlocked the potential of the maglev. The German builders of the Transrapid maglev system constructed a series of stator blocks that are the main component of the linear motor and act as the propulsion system for the train. Once installed, they were tested in Germany, and in combination with the support and guidance magnets, enabled this unique vehicle to levitate. Relocated to Shanghai, the maglev vehicle travels at well in excess of 400 kilometers an hour without an onboard engine.
A linear motor is embedded into the guideway for its full 30 kilometers. But don't be fooled into thinking this whole track is electrified all the time. What is so brilliant about this system is that only the sections of the track on which the vehicle moves is powered at any time. So as it sets off, the 30 kilometers of track ahead of it is dormant, and only the section in front of the maglev turns on. As soon as the maglev has passed over the short section of track, it turns off again, as the job of pushing the maglev along is taken up by the next section of track, and so on, all the way to its destination.